Um, Thank you. I'd like to thank first Professor Yu and the rest of the organizers for inviting me to speak here. I'm happy to talk to you today about the middle product learning with errors problem. So this talk is going to be based on some series of work with several collaborators, as well as some other references. And the latest one here is, in fact, still a work in progress, which is in submission. Okay, so what I'm going to do is I'll start for this first talk by introducing, first of all, the kind of approach that is behind this new product learning error problem. And that's what I call the risk-performance balance approach to lattice crypto. So this is really the main motivation for all this problem. And so once we understand this motivation, we can see, we can learn a bit about the foundations of this approach. So I'll focus on, in fact, two problems besides the problem in the title of the talk, which is MP-LWE. In fact, there is a kind of dual problem called the polynomial cis problem, or what I call thesis null. And these two problems are kind of analogous to the LWE and cis problems that are the basics of lattice crypto, but these are the variants for this approach. And so I'll talk about both of these because they are both important for the security of constructions using this approach. So I'll start with the polynomial cis problem, which is in fact the original problem that was investigated first for this approach in 2016 by Lubashevsky. And the nice result about this is that the hardness of this polynomial cis problem is as hard as the normal ring cis or polynomial cis problem defined over some polynomial f for a large family of f's. So this is really the nice result that started this type of work. So after we look at how this works, we'll see also some of the known attacks on this problem. And we'll see also some variants that are needed in the actual applications of this problem that I'll talk about in my next talk. So these are the inhomogeneous variant of this problem. And then for that problem, we can look at it with various parameter settings like large secrets, as I call it, and small secrets. And we'll see that there is significant differences in the hardness between these two regions. And then we'll go to the middle product LWE problem, which is a kind of dual of this one. And we'll see, first of all, the motivation for how it was defined and some ways to interpret it. And then we'll see the reduction from Roska et al. From 2017, which is a kind of an analog of this result for cis. And then we'll briefly discuss some of the variants of this problem that have been introduced. And we'll see some known attacks and some other, also this behavior of how this problem varies with the parameter sizes. And I'll finish up by giving some open problems. And I'm happy to also answer any questions during the talk. Okay. So let me first introduce this approach. So of course this whole workshop is on lattice-based crypto, and you've already seen these nice properties of lattice-based crypto, a high efficiency of computations, very powerful crypto systems that can be constructed from these things, and also very powerful security guarantees we can get for these crypto systems. And finally, this conjectured security against quantum attacks. So all these things are very nice properties, and of course you've already seen the definition of a lattice, so I won't go through this too much in details. As we've seen many times in this conference, the hard problem underlying lattices is finding short vectors or approximate shortest vectors in lattices. And we know that even quantumly this problem seems to be hard and seems to take essentially exponential time in the dimension. But an important thing to realize is that in fact the hardness of lattice problems really is may be very crucially dependent on the choice of the particular lattice. And so some lattices can be much easier than others. And so that's something that causes a lot of kind of controversy in lattice-based cryptography. Which lattice can we trust for these problems to be hard? And so the traditional approach that started off lattice crypto which is what I call the LWE or unstructured approach. So it started with this work of Aitai and then Regev that introduced the CIS and LWE problems. And then both of these works were able to show very nice reductions from worst case approximate shortest vector problem in any lattice. So that if these problems are easy, basically all lattices are easy under the shortest vector problems, or approximate shortest vector problems. So that's really the ideal type of lattices to use, because it means that as long as some lattice class of lattices is hard, then we know that these problems will be hard, and we can base all these nice crypto applications on them. And so the LWE problem, as you know now quite well, can be written in this form in the search variant. So given a matrix A and a vector Y that is A times a secret plus a small noise, is to find that secret S. And so the main advantage of this approach is its low security risk. The lattices that we rely on have no structure. It's worst case lattices if we use this reduction. And so it's a very low security risk. But the drawback is a relatively low performance, so that if we look, for example, at this matrix A in the LWE problem, it has m times n integers in it, and this is already, just to read this matrix takes time, which is quadratic in n. And so the running time is not as nice as we would like it to be, and also storing such big matrices tends to be a drawback. So that's the disadvantage of this approach, and despite this, there have been a lot of attempts to make practical crypto systems based on this low security risk approach. And Frodo, that is one of the candidates in the NIST competition, is one of those approaches. And using various optimizations, it can get reasonably good performance. but it still lags far behind other more structured lattice approaches. And so this is the motivation for looking at structured lattices, like the most common ones are lattices that come from polynomial rings. And their corresponding problems are sometimes known as polynomial LWE and polynomial cis, and sometimes they are known as ring LWE or ring cis. There is some difference between how these are defined, some technical differences, but they are closely related. So these works showed that if you use this algebraic structure, you can still get some strong security guarantees. So there are reductions from solving approximate SVP in a class of this kind of algebraic lattices, or ideal lattices, for example, to solving these polynomial and LWE and cis problems. But of course now, the security of these problems rests on the hardness of a worst case class of lattices in this restricted set, which has an algebraic structure, which is a polynomial structure. And so it is a kind of a higher security risk approach in terms of security, because maybe there is a fast algorithm to solve SVP, approximate SVP in these structured lattices. Mostly so far, we don't know a lot of attacks on these structured polynomial LWE and polynomial cis problems, but we have seen some attacks that exploit the structure on this kind of ideal worst case problems. And I'll talk a bit more about this in a moment. So the problems that we use in cryptography based on this approach, they look something like this. So you have the same kind of definition of LWE we saw before, but this time this matrix A is in fact a matrix of polynomials over a ring of polynomials that is typically something like this. So we work with coefficients in ZQ and modulo a polynomial like x to the n plus 1. So the advantage of this approach is that because we are using polynomial rings, all these arithmetic operations here, in fact, can be done very quickly using fast arithmetic like FFT-based approaches. And so their effect can be done in time that is almost linear in the dimension rather than quadratic in the unstructured approach. But the drawback of this approach is, as I said, that we are relying on very specific kind of lattices. And in particular, the kind of problems that we typically use in this type of systems, like New Hope, for example, is rings modulo a very specific polynomial like x to the n plus 1. And so we are really relying for this fixed f on the hardness of this problem. And that's where the higher risk comes from. So just to illustrate the potential risk of basing our security on such structured lattices, we can look at some of the recent history of the approximate SVP problem, which is that worst case problem that that reduction was given between these problems. And that problem had a series of, there were a series of papers showing that the SVP problem restricted to these kind of ideal lattices is really seems to be much weaker than general lattices. And so these are, these works have studied various special cases like principal ideal lattices, and then they've been extended to more general ideals. And you can see that they can solve the problem efficiently here in quantum polynomial time for sub-exponential approximation factors. But this is still much higher than what we use in lattice cryptography, that is polynomial in the dimension. So it doesn't yet threaten any practical systems, but it does show that there is some risk, and maybe future developments will make this risk even bigger. And so, all this has motivated a lot of people to work on kind of lower risk approaches, but not as low as the unstructured LWE and SIS approach, which loses a lot in performance. So some of the approaches for this have been to use, for example, this ring LWE or polynomial LWE with non-cyclotomic modulus polynomials f. So instead of the x to the n plus 1 that I had before, they replaced with a non-cyclotomic polynomial that has presumably less structure. But again, these approaches still rely on a fixed polynomial, which also may have some specific weaknesses. So another approach that was used in recent times is what's called the module LWE approach. And what this approach does is it replaces the vector of polynomials of the secret in the original polynomial LWE problem. It replaces the single ring element in the polynomial LWE problem with a vector of polynomials of some dimension k. This is called the module rank. And so this is kind of trying to go somewhere in between polynomial LWE and unstructured LWE. But it's a kind of trade-off, and it's not even clear if it really lowers the risk, because we still stay with vectors of polynomials in the same ring with a fixed modulus f. So if that modulus somehow induces a weakness in this problem, it may be inherited by the module problem. And in fact, there are some attacks that show that you can effectively reduce the module version of the problem to the ring version. So it doesn't seem to buy you a lot of extra security to go to a module. So all these approaches still are based on a fixed modulus f of x. And so this raises the question of whether there is another approach that will avoid relying on just a single f. And so this motivated the work of Lubashevsky in 2016 to introduce this new kind of problem, PCIS, and later I will call it PCIS null. And this kind of PCIS is what Lubashevsky showed is that it's as hard as the hardest PCIS problem over specific rings f with respect to a very large family of f's. So as long as one of the PCIS modulus f problems in this family is hard, it guarantees the security of Lubashevsky's PCIS null problem. And the basic idea behind Lubashevsky's approach was to work in the polynomial ring with coefficients in the integers, but with no reduction modulus some other polynomial f of x. So no mod f. That's the basic idea. The nice thing is that with this approach, now, although we got rid of the fixed f, this kind of risk of fixing f, we still get a high performance if we build systems based on it, because the arithmetic in this polynomial ring can still be done with fast arithmetic. So this looks like a very promising approach to reduce the risk without compromising too much on efficiency. But of course, SIS is limited to be used for things like signatures, but we don't know how to use it for encryption. And so in the later work of RSS that I'll discuss later on, we introduced this kind of LWE counterpart of Lubashevsky's thesis null problem, and we called it the middle product, or MP-LWE, and we showed that it has a similar security low risk guarantee in that we can show that if you can break MP-LWE, you can break any PLWE mod F, again for a big family of moduli F. Okay, the basic idea here is to work again in this polynomial ring without reduction mod F, but with a twist that that we call the middle product, and I'll discuss it later. So then we showed that we can naturally use this new kind of LWE problem to construct kind of public key encryption, and we call this field titanium. It was also submitted to the NIST process. Later on, we designed some signature schemes based on this, and this we'll talk about in my next talk. So this is a kind of illustration of the relations that we show between MP-LWE and this huge class of polynomial LWE problems with a large set of moduli polynomials. So now that I've set the background, let me show you some more about these problems that are behind this approach. Before that, are there any questions?
My question is, what is the intuition behind the proof of Lubashevsky to remove the module operation in polynomial mathematics? And why does that improve the...
You mean in the proof, right? Or
but why does removing module F improves the...
well, so I will talk more about this later on, but basically by removing the mod F, we are kind of avoiding relying on a specific mod F structure. So it's kind of so the main reduction shows that Hardness mod F structures in many types of X, many types of rings. So that's kind of the intuition. But I also talk more about it. Okay. So if there's no other questions, let me move on. So let me show you first Lubashevsky's thesis null problem. So we're going to work in this polynomial ring mod F for the original ring sys or polynomial sys mod F problem. And this is the definition of the original PSys mod F problem. So it's quite analogous to the definition of sys in the unstructured case, but changing the ring. So here we are given a bunch of random polynomials, uniformly random in this ring mod F. And the goal of the attacker is to find a set of polynomials z1 up to zk, such that the sum of the linear combination of the AIs with the zi coefficients gives you the zero polynomial mod F, and the coefficients, the zi's, have to be short. Okay, so here we use the infinity norm for the shortness. And of course they have to be a non-zero set of polynomials. So in fact, this is a natural kind of approximate shortness vector problem in this kind of ring. Now, it's useful, before we talk about Lobachevsky's problem, to look at the polynomial, to look at another interpretation of this Cis mod F problem. And this is the interpretation using matrices. So if we write down a polynomial a of x in its n coefficients, if we write it down as a vector, and we take two polynomials a and z, and multiply them to get c mod f, then if we write out this product, we can expand it by the coefficients of z, and you can see that what we have multiplying the ith coefficient of z is the x to the I times a of x mod f. And so we can rewrite this expression in a matrix vector form, where we take the coefficient vector, here written as a row, and multiply by what we call the Roth matrix for A. And the Roth matrix for A, mod F, is exactly this matrix where the ith row of the matrix is, sorry, this should be an I here, is the coefficients of x to the I times a of x mod f. So if we take, for example, for the modulus f of x, the polynomial x to the n plus 1, then since x to the n is minus 1 in this ring, then what happens when we multiply by x, the polynomial, is that all the coefficients shift by 1 to the right, and the one that was the coefficient of x to the n minus 1 becomes the constant coefficient with a negative sign. And so we get this kind of cyclic or negacyclic matrix where each row is shifted by 1 with a negative sign. So this is the Roth matrix of A mod f for this particular f, but of course we can do it for any f using this definition. So this is another interpretation of the ring multiplication operation mod f. And so we can rewrite the polynomial Cis problem mod f as the problem of finding a vector of coefficients of the zi's, so that when we multiply it by a matrix, a kind of tall matrix that has these kind of Roth matrices of the AIs arranged in a column, gives you 0 mod cubed. Okay, so now let's see how Lobachevsky defined this polynomial problem. And it works like this. So, remember that the motivation for Lobachevsky's thesis null problem is that it should be as hard as thesis mod f for many f's rather than just a fixed f. So the main observation that Lobachevsky noticed is a very simple one, and it is that if you can solve, if you can find a linear combination of polynomials ai with small coefficients here that gives you 0 without reduction mod f, then of course if we reduce both sides mod f, then we get also a 0 mod f for any f that we choose, because the f doesn't affect anything as long as we have this original relation without the mod f. So this is really the intuition. So it led him to define his new problem, polynomial Cis null, in the same way as we did before mod f, except that now the AIs are polynomials of degree less than n, and you have to find a linear combination that is 0 without reduction mod f. So here we have an extra parameter d that tells you how big the degree of the coefficients that i's can be. Okay, and they still have to be short as before in terms of their norm. So this is really the definition of Lobachevsky's problem. And we can ask how can we write it in terms of matrices like we did for the mod F problem? Yes? On D? Yeah, so D has to be less than N. Yes. Yeah, it can be equal. Okay, so here's the formulation of this problem in terms of matrices. We can write again the product of polynomials, but this time without the mod F. So we have here we have a shift by a power of x of A of x without mod F, which means that the coefficient vector that just gets shifted further to the right into higher order coefficients. And what we get here is a triangle of zeros on the left and on the right. So the matrix has this kind of parallelogram shape of the non-zero coefficients of A with zero triangles. And it has equal elements along the diagonals. And so it's what we call a Toeplitz matrix that is equal along its diagonals. So this is a representation of the non-mod F polynomial product. And in our thesis null problem, we're taking a combination of such things. So this time, the matrix A will consist of a bunch of Toeplitz blocks like this, stacked up on top of each other, one for each of the AIs. Okay, and so here's the hardness reduction statement that Lubashevsky showed for this problem. So the reduction shows that the thesis mod F problem is the thesis null problem can be reduced from the thesis mod F problem for any modulus F as long as its degree is between D and N. So there can be a huge class of polynomials, of course, with this range of degrees. So here's the idea of the proof. So let's denote the degree of the modulus F that we start with by M. So now if we're given an instance of the thesis mod F with polynomials of degree less than M, let's look first at the case when M is equal to N. So in this case, the degrees of these A's are the same as what we have in an instance of the thesis null problem. And so what we're going to do is we're just going to take these AIs and just give them to the thesis algorithm, the thesis null algorithm. And that algorithm will give us these z's, the small z's that combine the AIs to 0 without mod F. And then we'll use Lubashevsky's observation to conclude that also mod F we get a 0. And then the only thing we have to argue is that these z's are also non-zero mod F. And so this is where we need the degree D to be less than M in order to make Z non-zero mod F. Yeah, I think that was what you were asking here. Yes, it has to be strictly less. Yeah, so because the degree is less than M, if it's non-zero, it will stay non-zero because the mod F doesn't do anything. Okay, and then to handle the the other case, when m is strictly less than n, then we can do a similar thing, but what we have to do first is the AIs that we get have a smaller degree than the AIs that our algorithm expects. So what we do is we lift the degree of the AIs that we have to AI prime of higher degree by adding random multiples of f. So here f is of degree m, and we want to get up to degree n. So we choose the multipliers to have degree n minus m, and that makes the degree work out. And the other thing we have to check, well, first of all, does this argument we said before still work? Well, it does, because the AI primes are actually equal to the AI's mod f. And so what the algorithm gives us will still give us a solution to the original sys mod f. And the other thing we have to check is that the AI primes are going to be properly randomized here to be uniform in degree n. And this is not difficult to show. It's basically, if you look at the mapping from the RIs to the AI primes, then you can see that this mapping is going to be injective. And that means that the randomness of the RIs will fully randomize the AI primes. So that's really the idea of the proof. That was quite a nice result, and Lubashevsky went on to show how to construct a signature scheme from this problem that I'll discuss in the second talk. But let me now show you some of the known attacks on this problem. And of course, this problem, this species null problem is, well, it's a kind of sys problem, so we can use any generic attacks on the unstructured sys problem. But here, we can also improve things a bit, because we can take advantage of these zeros in the Toeplitz matrix, these triangles of zero that we saw. So the basic idea here is that if we remove from each of these Toeplitz blocks, if we remove some rows, so if we look at the Toeplitz block, if I remove, for example, this row here, then the number of non-zero columns shrinks by 1. You see that there's all the rest of the elements here are 0. And so effectively I've reduced the dimension of the problem. So this is the idea of optimizing of this attack, and we can choose this B prime to optimize the kind of attack that we get. And so if we do this and we look at the best known lattice attacks using lattice reduction, as was discussed earlier today. So if we formulate the actual lattice that we are finding short vectors in when we solve the species null problem, and we compute its determinant, we can estimate the length of the short vectors that the lattice reduction algorithm will give us if it has a certain root or mixed vector. And we get this kind of estimate, and you can see that basically what we have here is what we get in the standard sys problem. And this is an extra factor that is due to this extra dimension that we have. So as a consequence, the shortest vector that the attack finds if we optimize the choice of that T prime is larger by that factor of q to the 1 over k. So remember that k is the number of polynomials in the instance, and q is the modulus. So it shows us, for example, that if we have a small number of AIs, then the best attack is a bit harder than cis in dimension n. But as we have more samples, and in fact, when we have more than about log q's AIs, then the attack really becomes the same as cis in dimension n. Okay, but it's still interesting whether this factor for small k can be reduced, because small k is the most interesting case for efficient applications. Okay. Now, in Lubashevsky's paper, when he introduced the signature, he needed, in fact, to introduce some variant of this thesis problem, which is the inhomogeneous kind of variant of it. And basically, the way this is defined is that instead of having 0 on the right-hand side, we have some target value t, which is generated as a combination of some small secrets Si that are chosen at random from some interval. So we generate the target value as a combination of the AIs, and then we ask the attacker to find either the SIs, or in fact this is a relaxed version. The attacker can find even ZIs that are a bit longer than the SIs, and even we allow the attacker to have some multiple of t. So this is a kind of relaxed inhomogeneous variant. And so what Lubashevsky showed in his paper is that for sufficiently large secrets, so this parameter s that is the size of the coordinates of the secret, if it's large enough, in particular if it's large enough compared to q to the 1 over k, then there is a reduction to reduce the original thesis problem to the inhomogeneous variant. And and so this one gives us the hardness for this variant of thesis. And the main idea is basically to have the reduction that takes a thesis instance that it wants to solve. It will generate an inhomogeneous instance by choosing by itself these SIs and computing the target T, and then run the inhomogeneous algorithm to get another solution that is these Zs. And by subtracting the two solutions, the reduction can get these Zi primes that solve the homogeneous problem. And the reason why this reduction needs a large enough secret is that we have to argue that the Zi primes are not going to be 0. And essentially what we're using is that for a large enough S, this mapping from the SIs to the target T is a many-to-one mapping, so that we have multiple pre-images or multiple solutions to the inhomogeneous problem. And so it's likely that the attacker will give us a different one from the one that we chose when we generated T. And if he gives us a different one, then subtracting them will give us a non-trivial solution for the homogeneous problem. Now you might wonder what happens in the other case when the secrets are not so large, so that the inhomogeneous problem has a unique solution. And in fact, in the case of the normal cis problem, or even the polynomial cis problem mod F, this unique variant of the inhomogeneous cis problem is hard. In fact, it's as hard as polynomial LWE or LWE. But this is different in our thesis mod null problem. In fact, in the pieces null problem, this variant of the problem is easy to solve. It's no longer hard. And this is really a major difference to the other types of these problems, which causes some problems, as we'll see later. So, in fact, as soon as the S is small enough, essentially, to make the solution unique, the problem can be solved in time that is polynomial in everything except for k. So as long as k, the number of these AIs is small, then we get a polynomial time attack. And in practice, k is usually small, otherwise the system that we get from this problem is not efficient. So let me tell you the main idea. It's a very simple observation to this attack. And the idea is again to exploit these zero triangles in the Toeplitz matrix. And what we're going to do is we're going to reduce the problem to a sequence of k-dimensional knapsack problems. And since k is small, we can easily solve these problems just by enumeration, for example, or even by low-dimensional lattice reduction. So the main observation is that if we look at a linear combination of polynomials without the mod f, then for example, if you look at the constant coefficient of the target, it only depends on the constant coefficients of the secret polynomials. And in fact, this is the relation between the target constant coefficient and the secret. And you can see that here we only have k terms, and we can easily find the SIs, even though they are small, we can easily search that space of size, of small size to find the constant coefficients of the secret. Now once we have the constant coefficients, we can move to the next, the linear coefficients. These ones only depend on the constant and the linear coefficients. So if we already know the constant ones, we can remove them and search again a k-dimensional problem for the next coefficient, and so on. We can peel off the coefficients one by one. Okay. Okay, so now let me tell you about the middle product LWE problem. So, how should we define this problem if we were asked to do it? Well, the answer that we used when we were working on this is to look at what happens in the unstructured case if we look at Cis and LWE. In fact, if you look at what's the relation between these two problems, you can see it by looking at the corresponding lattices that underlie these problems. So for the Cis lattice, it's this perp lattice of the matrix A. So it's all the row vectors V that multiplied on the left of A gives you 0 mod Q. And the LWE lattice is you take the same matrix A and you multiply on the right your secret vector and add multiples of Q. So in fact, if you look at what the relation is between these lattices, it's a kind of duality relation of lattices up to a constant factor. But the lesson is that if you have a Cis problem with a matrix A, well, why not define an LWE problem by just taking the same A and multiplying a secret on the right. And so that's essentially how we get to the MP-LWE problem. We take for A the matrix that underlies the pieces null problem, the Lashevsky's problem. Remember that this matrix has Toeplitz blocks for the AIs stacked on top of each other. And in the MP-LWE problem, we take the same blocks of Toeplitz matrices and multiply by a secret vector on the right to to get the MP-LWE lattice. Okay, so this leads us to what is this middle product? Well, middle product is an operation that was defined for many years in computer arithmetic for polynomials. And all it means is if you have two polynomials A and B, and you multiply them to get the polynomial C, then instead of taking all of the coefficients that you get, you only keep a bunch of them from the middle part. So these ones in orange, and you throw away the other low order and high order ones. What you get is what's known as the middle product of A and B, and we denote it like this. So here D, the parameter D denotes the number of middle coefficients that we take out of the product. And it turns out that the middle product of polynomials is the polynomial interpretation of the middle product LWE operation that I explained before using the matrix A. So if you take the polynomials A and B and you compute their middle product, and you write the relationship between the coefficient vectors of the product, of the middle product and the A and B, then you can write it like this, and you can see that it's exactly the Toeplitz matrix that we saw before for A, multiplied on the right by the coefficients of B. The only thing that you have to take care of is that B is written in reversed order, starting from the higher order coefficients. And similarly, C is also written in the reverse order. But otherwise, it's just the multiplication by the Toeplitz matrix. Okay, so this leads us naturally to the definition of the middle product LWE problem. And it's defined analogously to the polynomial LWE mod F. So in the mod F case, we were doing the arithmetic in this ring with multiplication mod F. And now in the middle product LWE problem, we'll be given a bunch of AIs from degree n, and we'll also given these samples bi that are the AI times S, so there is a missing I index here. AI middle product S plus bi, and we have to distinguish these pairs from uniform pairs of polynomials. So that's the decision variant, and the search variant is to just find the secret S. So here is the hardness reduction that we showed for the middle product LWE problem. This is one of the statements of this reduction, which is actually tight in the sense that the noise distributions for the error and the secret are the same in both the PLWE mod F and the MP-LWE problem. So the reduction does not amplify the noise. There are other variants of this reduction that I'll mention briefly that do amplify the noise, but they allow for a larger class of Fs. So the main result is that PLWE mod F reduces to MP-LWE for any modulus F here, satisfying these conditions. So it's a bit more restrictive than the PLWE, than the PCS reduction of Lubashevsky, but it's quite similar. So we allow any polynomials of degree m between d and n. And in order to get this tight reduction, we also need some constraint on the highest coefficient below n in the polynomial f. But it's still a very large set of polynomials, and these conditions can be in fact relaxed, as was shown by these other works. So here's some of the other variants. So for example, in the original paper, we had variants where the error distribution was a continuous Gaussian with this standard deviation parameter, and P-LWE was also a Gaussian with a different parameter. And there we had some error amplification so that the parameter here alpha prime was bigger than alpha. But the amplification of the noise or the error is polynomial in the dimension when you choose the f from a class of polynomials that is sufficiently constrained. For example, to have polynomial size coefficients. So this is, yeah. By the way, in this variant of the problem, the secret distribution of both MP and P-LWE problem is just uniform. But in a more recent work, we extended this to what we call the small secret middle product LWE, and here both the secret and the error are chosen from discrete Gaussians with small standard deviations. So this is similar to the P-LWE mod F with small secret that is known to be hard in this case. Now I just mentioned that there are some generalizations recently by Pikert et al. Of the middle product LWE problem. So it was shown to fit into a kind of algebraic number theory framework, what are called number field lattices. And that work also generalizes our reduction to start from these number field lattices. And it allows for some relaxation of the restrictions on this family F of the polynomial of the modulus that we start from. And also recently, just in Asia Crypt last week or this week, there was a variant of middle product LWE that is called the learning with rounding variant, where the error distribution, instead of being, for example, a Gaussian, it's just obtained by rounding the middle product. So this is analogous to the LWR problem that was defined in the unstructured case, and they also showed a reduction from the usual non-rounded MP-LWE, but currently they can only do it for the search variant of their problem. So before I running a bit behind, but let me show you the main ideas for our middle product hardness proof. So the main idea that we use is this kind of relation between the middle product and the normal mod F product. So if we look at, remember that when we looked at the mod F product in these mod F rings, we could represent it by this megacyclic in the cyclotomic case, this rod F matrix of A, which had the coefficients of the shifted value of A of X mod F on its rows. So imagine that the rows here are the coefficients of X to the I times A mod F. What we want to do is we want to write it in terms of the Toeplitz matrix of A that we saw is the matrix that comes in the middle product definition. And it turns out that we can in fact relate these two matrices by multiplication on the right by another matrix, which is in fact also a Roth matrix, but in this case a Roth matrix of just the constant polynomial 1 mod F, and it has as many rows as columns of the Toeplitz matrix. And this relation here, which is easy to see from the definitions of these matrices, plays a crucial role in our security reduction between MP and mod F MP-LWE. So let me show you the idea of how we use it. So we start from the reduction takes samples from the MP-LWE mod F that look like this if we write them in terms of Roth matrices. So the Roth F matrix for B is the Roth F matrix for the A times the Roth F of the secret plus the Roth F of the noise. And we want to transform this into an MP-LWE sample. So what we do first is we take the first column of the matrix. So if you look at the Roth F matrix, it has on its first row the coefficients of the polynomial B. Well, what we want is in fact the first column of this Roth F matrix. And it turns out we can get that if we have a Roth matrix, we can get its first column by multiplying it on the left by another matrix related to the polynomial f that we denote by m sub f. And so if we do that, we're going to get that. So if we look at this relation on the top, the first column is equal to this matrix times the first column of this, which is mf times s, plus the first column of Roth Fe, which is mf times e. So we can rewrite the first column of the first top equations like this. And then we apply the relation that we saw on the previous slide to decompose the Roth F matrix into a product of the Toeplitz and this Roth F1 matrix. And so we end up with this relation here. And what you can see here is, in fact, if we look at this product here of these three matrices, in fact, this can be interpreted as a new secret vector S prime that is multiplied on the right of a Toeplitz matrix. And this mf times e can be interpreted as a new noise E prime. And so you can see that B prime, in fact, has the form of an MP-LWE sample, which is a Toeplitz times a secret plus noise. And so now, in fact, we have obtained our MP sample, which we can run the MP algorithm in the reduction. So that's the idea of the reduction. There are a few things that I didn't mention, which is we have to handle, for example, we have to make sure that the distributions here are correct and what are expected by the MP algorithm. So for A it's fine, but for E prime it's actually E multiplied by MF, so the distribution of E, this small noise distribution, will get kind of twisted by this multiplication by MF. And since it depends on F, the distribution of E prime here will depend on F, and it's not what we want, because in our middle product problem we want the distribution of E prime to be independent of F, since we want to reduce to a fixed problem. And so we handle this in the reduction by re-randomizing E prime in order to cancel out or to unskew this twist of MF. And this is a kind of standard technique in lattice-based crypto. Okay, so just to give you an idea of the kind of parameters that we can get for MP-LWE, this is a table of parameters that we used for our crypto system, Titanium, based on MP-LWE, and we chose these parameters based on the best known attacks to resist essentially 128-bit security, for example, in this column and other security levels. You can see the kind of dimensions we have are similar to what is used in normal the size of the family that we rely on in estimating the security based on our reduction, you can see it's a huge family of 3 to the power of 256 polynomials. And in this case, it even includes the cyclotomic polynomials that are usually used. Okay, so how did we actually get this table? What was the attack that we used to estimate the security? Well, we used a security based on the best known attacks of MP-LWE, and it turns out that this is a similar situation to what we had with PCs null. Basically, we can optimize the generic attacks on LWE by taking advantage of those zeros triangles in the Toeplitz matrices. So basically, yeah, once again we can chop off some of the last rows of the Toeplitz blocks, and it effectively shrinks the dimension of the underlying problem, and then again optimize the choice of that D prime that we keep. And so the conclusion, if we analyze this optimized attack, is again that we have a hardness gap relative to LWE in dimension n of q to the 1 over k. So it's a little bit harder, it seems, when k is small than LWE in dimension n. Okay, and just the last thing I want to mention for this talk is the inhomogeneous variant, or inhomogeneous species variant of the middle product. So this is a kind of name that I came up with to describe this problem, because it hasn't actually been used before so far until our recent work on a signature scheme based on MP-LWE. But basically the definition is similar to the inhomogeneous problem that we talked about for the PCs null problem. So in this case, the difference is that we replace these products by the middle products, and we still ask for a solution. And another difference is that here I take the target value in this inhomogeneous problem as a uniformly random value, and I again ask for to look at these two cases: one where there are multiple solutions or non-unique solutions, and the other one where there is no solutions with high probability. So it turns out that, maybe not surprisingly, that the kind of attack that I showed you before on PCs null with small secrets in the unique region, it has a dual in the inhomogeneous middle product variant. But because we go through a dual, it ends up being an attack for large coordinates this time, which makes this inhomogeneous problem easy. So again, the idea is the same: to reduce the problem to a sequence of k-dimensional problems. And so I won't go through the details, but it's kind of the dual of the PCs null problem. So in summary, what we've seen is this new variant from LWE and CIS called MP-LWE and PCs null that give us some kind of trade-off between the risk and performance compared to fixed modulus polynomial CIS and ring LWE problems. And still they have a higher potential efficiency in applications than LWE or CIS. And we also saw this kind of non-symmetric dependence of the hardness of the problems on the norm of the kind of variables. In the PCs case, a large secret was hard, a small secret was easy. But in the MP-LWE inhomogeneous case, it was the reverse. A large secret was easier and a small secret is hard. And so the problems that I think are interesting about these hard problems is can we, for example, get a variant of these problems with similar risk-performance balance features, but with a more symmetric dependence on the size of the variables in terms of hardness. So what we would like is that both scenarios of small and large secret gives you a hard problem. And this turns out to be very useful for applications, if we could have it. But so far we don't know how to do this. Another question is to investigate further the concrete hardness of these problems for a small number of these AIs, because as I showed you, the best attack is still a bit higher than what potentially it could be. And of course, another very interesting question is to study further the hardness of this MP-LWE problem and see if it could really be strictly harder than all the MP-LWE mod F problems. Because what we showed in our hardness reduction is that if one of these MP-LWE mod F problems in a big family is hard, it implies the hardness of MP-LWE. But the converse reduction we have not shown. So if even if all these problems are easy for all modulo F, we still don't know whether MP-LWE is broken, and it may actually remain hard even in that case, which means that it's even a lower risk security guarantee than what we can show so far. So these are a few questions, and I think since I'm already over time, I'll stop here for this. So thank you.